Okay. All right. So let's get back into heat transfer. So in this unit, we are kind of just going over the three different modes of heat transfer. And so, of course, we have conduction, convection, and radiation. Last time we talked about the governing equation for conduction, which is Fourier's law of conduction. And it looks like this. And did we do an example yet? No, not yet. Okay. So moving on today now to convection is governed by Newton's law of cooling. And so just to reiterate, I said this last time, but convection heat transfer involves the combined effect of conduction and advection. All right, so conduction is heat diffusion. So this is how heat moves in any medium that's not moving. So solids or liquids and gases that are stationary. And then advection is heat movement due to material movement. All right, so you can kind of think of this one as heat being carried along with a flow, for example. And so because of this, we can infer that the faster the fluid motion, the faster or the greater the convection heat transfer. All right, so the faster the fluid or moves, then the greater amount of heat transfer is, or heat is going to be transferred. All right. Okay, so if we take a little look at flow over a hot block, so if we have essentially a block of material here and it's hot, and we have a cooler fluid flowing over top of it, a couple of things happen. So I go through this in a lot more detail in the fluid mechanics course. But essentially what we have is a gradient of the velocity. So we know that our velocity of our air flowing over top of our plate is going to be 0 where it contacts the plate. And I'll explain that if you take 3,500. And then it gradually increases to the free stream velocity, so the far away fluid velocity. And then the temperature is going to be of the gas will be equivalent to the temperature where it's contacting the plate. And then it slowly cools off as it gets further away. Okay. So this is our temperature variation. And this is happening through both the fluid moving, carrying heat away from the plate, as well as heat diffusing away from the plate, as it would happen if the fluid was stationary. Okay. Just to remind you, for convection, there are two types. So there is forced convection, and there's also natural or free convection. All right, so I have two examples here for each. So under forced convection, the top left one is if we were wanting to cool off hot components on printed circuit bodies, for example, we could cool them off with having a fan forcing cooler air over top of those components. That would be forced convection because we are putting work into that system to move the air. If we wanted to have natural convection of those same hot components for our circuit boards, then we could just orient it differently and allow air to rise through it due to buoyancy effects. Okay, so if you remember, when gases get hotter, they become less dense, and so they tend to rise. And so that's what's driving the flow there. On the bottom row, we are heating water with a hot plate. All right, and so our convection, our movement of our air is happening due to this hot plate. So we're putting energy into the system through an electric hot plate. And then another example of natural convection would be cold water flowing through a pipe. And then the moist air is going to condense into water droplets on the outside. Okay. So kind of going back to this figure on the left, I have a few notes for you about that. So in the near wall region, velocity is going to be low, and the contribution to heat transfer due to conduction is what's going to dominate. All right, because our fluid is moving very, very slowly, so it's going to be mostly the diffusion or conduction portion of convection that is important. And then as we get away from the surface, our velocity gets higher, and energy transfer is primarily due to bulk fluid motion. All right. In the absence of any bulk fluid motion, heat transfer between a solid surface and the adjacent fluid is by pure conduction, and possibly by radiation. Okay, so if I go back to this picture, in the near wall region, so where velocity is low, heat transfer is due to conduction. So in this area, we're looking at mostly a conduction contribution. And then far away up here, this is primarily due to bulk fluid motion, so advection. Okay. So when we have convection, what we have is essentially advection and diffusion. And then what we have in the middle here is convection. Does that make sense? Okay. Okay, so rate of heat transfer due to convection is given by Newton's law of cooling. And this law looks like the following. So if we want to find our rate of heat transfer, Q dot, and I'm going to give this a subscript C for convection. Actually, you know what? No, hang on. We're going to call this like this because conduction also has a C. So I don't like just C. Okay. So our rate of heat transfer due to convection is going to be equal to H times A Ts minus T infinity. And I'm going to explain what each of these are in just one moment. All right, so if we have a plate and a fluid flow going over top of it, if this is the temperature of our surface, the temperature of our solid that's contacting the fluid, we're going to call this Ts. So this is temp of the surface. All right, so that is this term right here. And then the fluid is going to have some far away ambient temperature. So this is the far away fluid temperature. All right, so that is this term. And then I'm going to draw this kind of in 3D so I can show you what the area I'm referring to is. So the area is going to be the contact area between the solid surface and the fluid. So that is this frontal area here. All right, so we have our contact area between the fluid and the solid, which is right here. And then we also have this term H that shows up. So H is, H is our convection heat transfer coefficient. All right, this is going to have units of watts per meter squared Kelvin, or in English units, this would be BTU per hour feet squared degrees Rankine. And because of the denominator having Kelvin or Rankine, you need to use an absolute scale for the temperature difference. So whether Kelvin or Rankine, just depends on which H you're going to use, but you can't use Celsius or Fahrenheit. Okay. Okay. So something that's important to note here is that if you remember from our Fourier's law of cooling or conduction, we had K out front. All right, so we had kind of a similar form to the equation as what we just looked at for convection. So we have a coefficient out front times the temperature difference. K, the thermal conductivity, this is entirely a material property, right? The coefficient of convection is not a material property. Okay, so this is a big distinction. So this is not a fluid property. And instead it depends on several things. So it's going to depend on the fluid velocity. It's also going to depend on fluid properties. So it's not purely a fluid property, but it does take into account fluid properties. And then it also depends on the temperature and the geometry of the solid object. Okay, these heat transfer coefficients are often obtained using empirical correlations. So this just means experiments. All right. And in those experiments, what happens is we relate dimensionless convection heat transfer coefficients, known as the Nusselt number, to other parameters that H depends on. All right, so this is part of the reason why I like to separate thermodynamics from heat transfer. So K in heat transfer is a totally different thing than K in thermodynamics. H is now a totally different thing than it was in thermodynamics. So this is no longer enthalpy to us. This is a heat transfer coefficient. Okay? Okay. If you're ever in doubt, just ask me. Okay. So let's define the Nusselt number. So the Nusselt number is dimensionless, meaning all of the parts that go into it are going to combine to have no units at all. And it is defined as H over LC divided by K. And it is a function of fluid properties, geometry, velocity, etc. All right, where in this equation, LC is the characteristic length of the object. So this is often a diameter or length. All right. And H again is just the heat transfer coefficient. Oops. So this is our convective heat transfer coefficient. And then K is the same one that we had before. So that is our thermal conductivity of the fluid. All right, so it's important to note that this is of the fluid. All right, so when we're doing these problems, we have a solid object and a fluid. So we're talking about the thermal conductivity of the fluid, not the solid thing, okay? So for example, for forced convection, so if we have like a fan cooling off a microprocessor, for example, typically our Nussel number is going to be a function of the Reynolds number and the Prandtl number. All right. So for example, we would have that Nussel number is equal to some constant coefficient times the Reynolds number to some power n times the Prandtl number to some power m, where the Reynolds number is, wait, where's Josh? It's your namesake. Are you so excited? Do you feel called to this? Good. I'm so happy. So this is the Reynolds number. I think we have a Gauss in this class too, right? I don't know if they're here. And then another famous non-dimensional number. I was very excited. Richardson. Is there a Richardson? No, no one wants to fess up. Okay, that's fine. Those are cool last names for a fluid dynamicist. Okay, so our Reynolds number, I'm gonna very high level tell you what it is, but I talk about it a whole lot more in 3500 or in a fluid mechanics class. But the Reynolds number is the density times the velocity over some characteristic length scale divided by viscosity. And this gives a measure of turbulence in the flow. And then our Prandtl number is viscosity over heat capacity divided by K. All right, so both of these things, actually all of this, all of this is in ME 3500. Okay. So essentially, for convection, finding H depends on the fluid flow heavily. You don't know about fluid flow yet, so we have to save that for 3500 after you do know about fluid flow, and then I will talk about this in extensive detail. But this is essentially how it works, okay? So for this class, generally speaking, you'll be given H for the problems that you're going to solve, okay? Okay, so let's do an example. Okay, so we have a silicone chip measuring 5 millimeters on one side and 1 millimeter in thickness, embedded on a ceramic substrate. At steady state, the chip has an electrical power input of 0.225 watts. The top surface of the chip is exposed to a coolant whose temperature is 20 degrees C. The heat transfer coefficient for convection between the chip and the coolant is 150 watts per meter squared degree C. If the heat transfer by conduction between the chip and the substrate and the heat transfer by radiation are negligible, determine the steady surface temperature of the chip in degrees C. Okay. All right. So let's break this down a bit more. There were a lot of words there. Okay. So I'm going to redraw this picture. And I'm going to synthesize all of that information into my picture. So I have this little chip. Its thickness is 1 millimeter. And then I'm going to call this L is equal to 5 millimeters. And we also, this is not drawn to scale, obviously. So this is also 5 millimeters. Okay. We have coming into this little block is W dot in, which is equal to 0.225 watts. All right, so this is our power input into our little chip. And we know that heat is going to be leaving our chip. And it's leaving due to convection. Okay, so we have fluid moving over top of this thing. All right, so this is our coolant. And we're given that the temperature is 20 degrees C. So this is that T infinity that I mentioned in our equation. And I guess it's called T infinity in the problem as well. And then we're also given that the heat transfer coefficient for convection, so this is H, is 150 watts per meter squared degree C. Okay. Okay, so what we want to find is the following. So we want to find steady state surface temperature of the chip. All right, and so this is our variable TS in Newton's law of cooling. Yeah.
Is it degrees Celsius or is it Kelvin?
It's degree C. So you can, H can be presented as watts per meter squared degree C or K. So I take it back. You don't always have to use Kelvin or Rankine. You just have to be consistent with the units. Thank you. Okay. All right. So what ideas do we have about how to start this problem? What equations might we want to use? And what kind of a system might this be? Open or closed? Newton's law of cooling, yes, I agree. What about the open or closed system? A closed system? Okay, what is your closed system? I agree with you. Just the chip, right? Yeah, so if we say our system is just the chip, then it's a closed system. All right, and that's what I would recommend doing. Obviously, there's air moving in here, so if we drew our box bigger, it would be an open system because we have air coming in and out. But this system will work really well for us. So we're gonna do a system that's closed, and it's just the chip. Okay. Our governing equations are Newton's law of cooling So we have that Q dot of convection is equal to H A Ts minus T infinity, right? And we want to find Ts, right? So we want to find this. And we are given T infinity. We're given H. We can calculate A, right? But we don't know Q dot. So we have one equation, two unknowns. Any ideas on another equation we might be able to make use of here? Dig deep and think about closed systems. And also think about how we're given a power input. Yeah, so we're going to use conservation of energy. So we're also going to use conservation of energy for a closed system. All right, so that looks like dE dt is equal to Q dot minus W dot. And remember, Q dot for our system is Q dot in minus Q dot out minus W dot out minus W dot in. Okay. So we know from our problem statement that we only have Q out, not Q in, right? And we also only have W dot out, not W dot in. That makes sense? Okay, great. So that means, oh, and one more thing. We're assuming this is steady. So this goes to 0, right? So that means our conservation of energy equation gives us that 0 is equal to minus Q dot out minus W dot out. Oh, wait, we have work in, not work out. Sorry. No one stopped me. No one stopped me. That was a test. I'm just kidding. Sorry about that. Okay, we only have W dot in, not W dot out, right? So it's plus W dot in. All right. So we know that Q dot out is equal to W dot in. Right? Okay, great. And we know that W dot in is 0.225 watts. So I can take this and substitute it into here. All right, because our Q dot out is just our Q dot for convection. All right, so I'm going to plug that in and I will solve this now for TS. So I have 0.225 watts is equal to H, which is 150 watts per meter squared degree C, times our area. What area should we use? So we have a block, and there's 6 different areas that we could choose from, right? The top one, right? Okay, so we have 5 times 5. So we have 5 millimeters times 5 millimeters. And then we have TS minus T infinity, which is 20 degrees C. Since our H is in terms of C, I'll leave it as C. And that means that our surface temperature that we solve for is going to be in terms of C as well. Okay. I need to divide this thing by 1000 squared to get rid of my millimeters into meters, right? Yeah. Well, I need to divide each length by 1,000. So I have to do like 5 millimeters divided by 1,000 and then 5 millimeters divided by 1,000. So does that make sense? Do you believe me? Because I can do it. I can do it in another step. Are you sure? Okay. All right. Okay. So when we do this, we get that TS is equal to 80 degrees C. Any questions on that one? Not too bad? Okay. Okay. Now we're going to go back to radiation, which we briefly talked about last time. And the equation that governs radiation is called the Stefan-Boltzmann law of radiation. So radiation represents the energy that's emitted by matter due to changes in the electron configurations of the atoms or molecules, and then it's transported as electromagnetic waves or photons, which we already talked about. And so the maximum amount of thermal radiation that a surface at a temperature T greater than absolute zero can theoretically emit is called black body radiation. And it comes from the Stefan-Boltzmann law. All right, which looks like the following. So we have Q dot emit max is equal to sigma times area times temperature to the fourth. All right, so this is our little body with some area A, and it also has a temperature. And then it is emitting a heat flux. Okay, so in this equation, we have this sigma here that is the universal Stefan-Boltzmann constant. Oh. And it has a constant value, which is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Area is again the area of the body. So this area is just the area of our body, of course. And then our temperature is the temperature of our body in an absolute scale. All right, so our constant is per degrees Kelvin, so this has to be the absolute scale temperature. So this is the temp of the body in absolute scale. Yeah.
What a different concept for English is? Or do you just convert it?
Definitely you could convert it, and I'm sure it's somewhere in a table or in the book. I don't know it off the top of my head because I prefer SI units. Okay. All right, great. So real bodies are not going to generally emit the theoretical maximum amount. They'll emit something less than that. So some fraction less than this amount at the same temperature. So this fraction less is known as the emissivity of the body. It's given the variable epsilon. So this value is always going to be between 0 and 1. So you can kind of think of it as an efficiency. So it's a measure of how efficiently a surface emits energy relative to a black body. And it's going to depend on temperature and the surface properties of the material. Okay, so when we have emissivity for a body, that means that our actual heat transfer due to radiative emissions is equal to what we had before. So it's equal to the black body radiation times this emissivity. So we take our max possible radiation and then we scale it by the efficiency of that material. Does that make sense? So that's still our theoretical max, and then we scale it by the emissivity. Oops. Okay. There's another important radiation property, which is called the absorptivity. This is given the symbol alpha. And so this is the fraction of the radiation energy incident on a surface that is absorbed by the surface. Its values range between 0 and 1, just like emissivity. And when alpha is equal to 1, this represents a black body. Okay, so if we have some incoming radiation onto a surface, so I'm going to call this Q dot incident. So this is some incoming radiation. What will happen is this will break into two parts, essentially. So it will get binned. So if we have some incoming radiation, oh my gosh, that's bad. All right, so here's our incoming radiation. Some portion of this is going to be reflected. And then another portion of it will be absorbed. So this is Q dot absorption, and it's equal to alpha times the Q incident. And then this one is the reflected, and it is equal to 1 minus alpha QI. Does this picture make sense, or should I draw it bigger somewhere else? It's okay. Okay, so essentially alpha is telling us how much is going to get reflected and how much is going to get absorbed. And we know that incoming radiation is going to equally, or it's not equally, it's going to fully split between those two things. So both of those two buckets, when you sum them back together, you'll get the incoming radiation. Okay. Okay. Kirchhoff's law of radiation states that emissivity and absorptivity of a surface at a given temperature and wavelength are equal. So essentially this is saying that alpha is equal to epsilon. All right. And we have standard values for emissivity listed in the table right here. This is from the book. So our emissivity is going to be very low for things like metals, like aluminum foil, copper, gold, silver. And then as you move down this list, your emissivity increases for things like water, soil, vegetation, wood, human skin. Weird thing to list in a table, but yes. Okay. Okay. So for the special case of a surface that's exposed to large surroundings of uniform temperature, which I'm going to call T surroundings, the net radiation exchange rate between the surface and the surroundings is given as the following. So we have, this is frustrating. Okay, so we have Q dot of radiation is equal to emissivity times that universal constant times area, the surface temperature to the fourth power minus the surroundings to the fourth power. All right, so these are absolute temperatures. Okay. Okay, so if we look at this little picture here, if we have our little plate that's being heated, we have Q dot of radiation coming out like so. And our material properties are the emissivity, the area, and then the surface temperature. So that's all of the things that are in what I call purple. So our emissivity of our material is this guy right here. We still have our universal constant. Our area is this guy right here. And then our surface temperature is right here. And then the very far away surroundings are T sur or T surroundings. So that's this. Okay. Okay, so if we want to find the net rate of heat transfer by radiation between two surfaces, that's actually pretty complicated. And that's because it depends on the properties of the surfaces as well as their orientation relative to one another. And the medium between them. Oh, sorry, and the interaction of the medium between them. All right, so most gases do not interfere with radiation, but liquids are typically strong absorbers of radiation. Okay, so this idea of finding the net rate of heat transfer by radiation between two bodies with a medium in between them can get very hairy very quickly. So in general, the net rate of heat transfer by radiation between two surfaces separated by a non-participating fluid medium, so a gas, will depend on the view factor of the surfaces, as well as the fraction oh, I'm sorry. I did view factor too soon. The next one is view factor. So it depends on the emissivity. Sorry about that. Of the surfaces as well as the view factor between the two surfaces. So view factor is just the fraction of the radiation leaving one surface that's absorbed by the other or intercepted by the other. Okay. All right, so if we have this circumstance to the right here, if we wanted to find the rate of heat transfer due to radiation uh, from surface 1 to 2, this would look like this. So we would have sigma T1 to the fourth minus T2 to the fourth divided by a big denominator that looks like 1 minus epsilon 1 over epsilon 1 A1 plus 1 over A1 F1 2 plus 1 minus emissivity of 2 divided by epsilon 2 A2. All right, do not worry about this equation. If you are interested in radiation, there is an elective course that covers it, and it is ME 4520. So this is intermediate heat transfer. So I will not be expecting you to do anything with that equation. This is just an FYI. And a teaser for those of you who really love heat transfer. Okay, let's do a break, and then I have an example, I think a couple of examples to do afterwards. Thank you. Okay, so let's do a couple of examples and practice using these equations. So in this first one, we want to consider a person standing in a room that's maintained at 22 degrees C at all times. The inner surfaces of the walls, floors, and ceiling of the house are observed to be an average of 10 degrees C in the winter and 25 degrees in the summer. We would like to determine the radiation heat transfer between the person and the surrounding surfaces if the exposed surface area and the average outer surface temperature of the person are 1.4 square meters and 30 degrees C, respectively. Okay? So let's annotate this little figure here with what we're given. So our surroundings are 10 degrees in winter and 25 degrees in the summer. So essentially we're going to solve this problem twice, once for summer conditions and then once for winter conditions. We also have that the person has a temperature of 30 degrees C, so this is TS. Our person is our surface. And then we know that the area of this person is also 1.4 meters squared. Okay, so we want to find Q dot radiation. All right, and we have an equation for this, so we can use the Stefan-Boltzmann equation. So we have Q dot for radiation is equal to epsilon times sigma times area times the surface temperature to the fourth power minus the surroundings temperature to the fourth power. All right, and we also, so let's look at what we have. So we have the area of the person is given to us. We have the surface temperature of our person is given to us. And we also have our surrounding temperature given to us. Sigma is a constant that is always the same, so we know that one. We don't yet have emissivity, all right? So we're gonna go to a table to find that. And it's a little bit earlier in the notes. So we're gonna use table 9.6. Anybody have an idea for what emissivity we should use? I know, yes, we should. I don't know why, it grosses me out, but yes, that's what we're gonna do. We're gonna use the emissivity for human skin, which is 0.95. I guess it's relevant for like sunburns and stuff, but I don't know. It's weird, right? I'm not the only one. Okay. All right. So now we have everything that we need to do, so we can find Q dot of radiation for the winter by using all the values that we have now, and we're going to use the T surroundings temperature for winter. So we have our emissivity, which is 0.96 times sigma, which is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth, times our area, which is 1.4 meters squared, times our surrounding temperature, or our surface temperature, sorry, which is 30 plus 273. So this is to get into Kelvin to the fourth, minus 10 plus 273 to the fourth. All right, and so these are units of Kelvin to the fourth. Kelvin to the fourth. All right, and we get 152 watts for the winter. And if we do this exact same thing for the summer, so all I'm doing is repeating this same calculation, but with the surroundings temperature is now 25 degrees C instead of 10. And we get 40.9 watts. Any questions on how to do that? Pretty friendly, right? That's not too bad. Yeah. What's the what? What?
So the problem. Like, what does that mean?
It's a red herring. Unnecessary information. So that would only be important if I also asked you about convection. This is a book problem. I dislike when book problems do this to me, but you know, it happens sometimes. Other questions? Okay, let's do another example. So this one has kind of like a little prelude with interesting information in it. So we're gonna talk about thermocouples for a second. So a thermocouple junction can be approximated as a small sphere, and this is what's often used to measure the temperature in a fluid stream. So a thermocouple consists of two wires made of dissimilar materials. So for example, you would have copper and constantan. And when they're joined together, an EMF or an electric potential is generated between those two dissimilar wires. And then the potential is going to vary with the junction temperature. And this is known as the Seebeck effect. All right, so if we assume that a thermocouple is used to measure the steady temperature of the gas flow in a combustor, the steady thermocouple reading is 1,000 degrees C. The walls of the combustor are at 200 degrees C. The heat transfer coefficient between the thermocouple and the hot gases is 200 watts per meter squared Kelvin. If we neglect conduction through the thermocouple wire and evaluate the actual steady temperature of the gases, or we want to evaluate the actual steady temperature of the gases, we can assume that the thermocouple has an emissivity of 0.9 and that all other surfaces behave as black bodies. Okay, so I'm going to draw this as a picture. So our thermocouple is a sphere, and then we have two wires connected to it. Like so, and I'm going to make the thermocouple our system. So there's our system. So we are going to have Q dot of convection, and we're also going to have Q dot of radiation. All right, we know that the temperature of our surface, which is the thermocouple, is 1,000 degrees C. And we know that air is coming through here. So we have T infinity out here and H, and this is air. And then our walls are heated. So we have that T temperature of the walls is 200 degrees C. And we were given in the problem, we have that the heat transfer coefficient between the thermocouple and the hot gases. So this is a convection heat transfer coefficient. So this is H. So this is 200 watts per meter squared Kelvin. And then for radiation, we also know that the emissivity of this body is 0.9. Okay, so we want to find the steady gas temperature. So we want to find T infinity. All right. So let's talk about what happens with the thermocouple. So the thermocouple is losing heat by radiation to the walls. And it's gaining heat by convection from the gas. Okay, so our radiation is going to be governed by the following. So we have Q dot rad is equal to emissivity times sigma times the area, temperature of the surface to the fourth minus temperature of the wall to the fourth. And then our convection is governed by the following. So we have Q dot convection is equal to H A T infinity minus T S. So I want to make a quick note here because in the notes, I don't really love the way that I've done this. I think it might be confusing. So if we have a surface and heat is leaving the surface for convection, this is HA TS minus T infinity. Okay, so this is when the surface temperature is greater than the ambient temperature. And then if we have the opposite situation where the air is heating the surface, this is HA T infinity minus TH. Okay, or TS, sorry. Does that make sense? So that's why I am using T infinity minus TS because we're assuming that that Q dot term is coming into the body. Okay. Okay. So we also should look at conservation of energy to kind of organize ourselves with these Q dots that we have coming and going. Okay. So conservation of energy for a system at steady state, we have the following. So we have dE dt is equal to Q dot minus W dot, where Q dot is Q dot in minus Q dot out. And then W dot is W dot out minus W dot in. Right? Okay, so we don't have any work moving around in here. So there's no work, at least not that we're told about. And our input heat transfer is convection, right? So Q dot in is Q dot convection. And then our output Q dot is Q dot radiation. All right, so what we have here, so this is 0 since it's steady. All right, so 0 is equal to Q dot of convection minus Q dot radiation. Right? And we can rewrite this to say that Q dot convection is equal to Q dot radiation. Okay? Okay. So I am going to substitute in my equations that I had written before. So I'm going to take my Q dot convection equation and I'm going to put it in here. And I'm going to take my Q dot radiation equation and put it over on this side as well. All right. So when I do that, I have the following. So for convection, I have H times A T infinity minus TS. And this is equal to epsilon sigma area times TS4 minus TW4. All right, and we are trying to find the ambient air temperature. So we're trying to find T infinity, right? Let's look at what we have. So we already know H. We already know the surface temperature. We know emissivity, and we know sigma, and we know the temperature of the walls. We're not given any information about area, but that's just fine because it cancels out, right? So we can just cancel these out and then solve for T infinity. So we have T infinity is equal to emissivity times sigma divided by H. And then we have TS to the fourth minus TW to the fourth plus TS. All right, so I'm going to plug in all of those values and we get the following. So we have 0.9 times 5.67 times 10 to the minus 8. You guys must really love that constant, don't you? Meters squared times k to the fourth divided by 200 W over m squared k. And then I have quantity of 1000, and this is degrees C, so I have to convert it to Kelvin. So I add in that 273, and then I subtract off the 200 degrees C, also converted to Kelvin to the fourth power. And then last but not least, I'm going to add in my surface temperature, which is 1000 plus 273. Okay. And so I get that T infinity is 1657.3 degrees C. Okay. All right. So one thing that I want to also mention is if you were to set up this problem and say that, well, I think Q dot convection also points out, that's fine. So if you did that, then essentially what would happen is you would have two outputs and you would have used the H times A times the quantity of TS minus T infinity. And you would have had both of them as outputs. So you would have picked up a minus sign because you said it was an output, and then it would all come out in the wash and you would still get the same temperature because it would just turn out that the arrow points the other way. Okay, so if you guess wrong with the direction of the Q dot, it's A-okay. All right.